Awesome. So, yeah, good morning, good afternoon, or good evening to all, and welcome to Data Driven Community Virtual Meeting. A few words about Data Driven Community. If you will check the community website, then you can notice we are managing two branches of activities. Scroll down to the page a bit to see the upcoming events. On the left side of the page, you can notice the Future Data Driven Summit, an annual joint conference we are leading and running with multiple data platform user group partners. The second branch of activity are weekly meetings of the Cloud Data Driven User Group, like today. And you are more than welcome to contact any of the community board. Jean Joseph is the founder and co-administrator. Ronan is the second co-admin. Anna Wikes is the third moderator. My name is Deepthi Goguri. I'm the fourth moderator, and I'm a database administrator and a Microsoft Data Platform MVP. I'm the third co-admin of the data-driven community, and I will be hosting this session today. If you'd like to contact me, you can scan the QR code here. Today, we are here to help and serve the data platform community. During the meeting today, please feel free to use the chat for any questions and discussions as well. You're also welcome to use the reaction. It doesn't interfere with the course of the meeting. If you hear something you love, like, or you want to clap hands, then feel free to do so. Today, we are very honored to have Klaus Aschenbrenner with us. He's the owner of the SQL Passion, a SQL Server consultant and training services across Europe. Klaus worked with SQL Server for more than 20 years. We would like to welcome Klaus today. Awesome. So I think, Klaus, let me go ahead and you can go ahead and share your screen right now and get started.
Okay, thank you. So hello everyone, and thanks for attending my session about exploring PostgreSQL for the SQL Server developers and database administrators. As you have already heard, I'm working with SQL Server for more than 25 years. And over the last year, I have also concentrated a lot on PostgreSQL. And today is the first time in my life that I'm talking in public about PostgreSQL. So I'm already looking forward how this session will go, but I think it will be very, very funny. So a few words about my person. My name is Klaus Aschenbrenner. I'm based in Vienna in Austria in Europe, and I provide with my company SQL Passion, SQL Server consultancy and training services across the whole world. I'm specialized in the relational engine of SQL Server. So my main topics in SQL Server are mostly performance tuning, performance troubleshooting, high availability, disaster recovery and all those things. And over the last year, I've also concentrated in more detail in PostgreSQL because it seems these days that Microsoft doesn't invest that much time in SQL Server anymore. And therefore, it was for me the time to also look into other databases like Postgres. I'm also a Microsoft certified master for SQL Server. I have also written the book Pro SQL Server 2008 Service Broker, which was published by APRIS in the summer of 2008, so already a very, very long time ago. Service Broker is an asynchronous messaging framework that Microsoft provided first with SQL Server 2005, and with Service Broker we can implement distributed message-based database applications. You can find more information about my person, the services that I'm offering on my website, sqlpassion.at, where I'm also regularly blog about SQL Server, about Postgres, and also other IT topics. Let's talk now a little bit about the agenda. we have about 75 minutes, and for the next hour, I just want to give you a brief introduction into Postgres. And my goal is just to show you how Postgres differentiates from SQL Server and how the concepts that we know from SQL Server maps into Postgres. It's not a really deep dive session into Postgres, it's just a brief overview so that you can start working with Postgres. So in the first step, I just want to give you a brief overview about Postgres, what is Postgres, how it relates to SQL Server. Then we will talk about the whole architecture of Postgres, which is more or less completely different than the architecture that we know from SQL Server. Then we will talk a little bit about querying data. So I will explain execution plans to you, data access methods. I will also talk a little bit about indexing. And in the last part, I want to talk about the multi-version concurrency control system that Postgres employs. And this concurrency control system is used for concurrency. So when you have multiple queries which are concurrently reading and writing, and as we will see here, Postgres handles concurrency in a completely different way than SQL Server. So let's talk now in the first step about Postgres itself. What is Postgres? Well, Postgres is just a relational database engine. So more or less, Postgres is the same as SQL Server. It's just a relational database engine. But the most important difference is Postgres is open source. So the whole source code of Postgres is hosted on GitHub. You can download that repository and you can just look into the implementation of a relational database engine. Postgres is completely written in C. As we know from SQL Server, for example, SQL Server is mostly written in C++. Parts of SQL Server are also written in assembler, so with machine code, but SQL Server is closed source, so we have no idea out of the box how SQL Server performs some special things in the background, because in that case we would have to disassemble the whole binary code of SQL Server. And here with Postgres, you can just look into the code base. So when you have questions, how things are working, why Postgres is doing things in that way and not in that way, you can just look into the code base, which is open source. Of course, you need a very, very good understanding of C, the programming language, because yeah, this is a really huge code base, and in the first step, it's a little bit more complicated. The whole source code of Postgres is maintained by the PostgreSQL Global Development Group. Means those are just people which have wide access to the repository, means they are able to push changes that other committers are making to the code base into the main branch, and they are also responsible for releasing new versions of Postgres. The initial release of Postgres is already decades ago. The first initial release was in the year 1989, and in that area, the database was called Postgres. Postgres itself was developed by Michael Stonebaker at the University of California in Berkeley, and Postgres was just a successor to the Ingress database system. And now we have more than 20 years of community development, and in the year 1996, Postgres was also renamed to PostgreSQL, because in 1996, PostgreSQL has also got support for SQL. So the programming language that we are using in SQL Server. In SQL Server, we have T-SQL, Transact SQL programming language, and PostgreSQL also uses a SQL dialect. But as we will already see today in my session, the SQL dialect that PostgreSQL uses differentiates a little bit from SQL Server. So this is also very, very important. When you want to migrate from SQL Server to PostgreSQL, you also have to rework your queries because some things are not working in Postgres, because SQL Server sometimes just implements things differently, which are not part of the official SQL specification. And today we have Postgre version 17.2, which was released, I think, a few weeks ago. So this is already a really major release of Postgres. What are the features of PostgreSQL? More or less, it's just a relational database engine. That relational database engine can be used for OLTP workloads, online transactional workloads where you're reading and writing. Means you can have concurrent read and write requests. And as I've already said previously, one key differentiation of Postgres is the fact that Postgres uses a multi-version concurrency control system. As we know from SQL Server by default uses pessimistic concurrency, means reader select statements are requiring shared locks. Every time when you make modifications in your database, so when you perform insert, update, delete statements, SQL Server requires an exclusive lock. Both locks are just incompatible to each other, leads to blocking situations. Means in SQL Server by default, a reader blocks a writer blocks a reader, and a writer always blocks a writer. A reader doesn't block a reader. So by default, with pessimistic concurrency in SQL Server, we have a huge amount of blocking situations. We can have a huge amount of deadlocks. And therefore, beginning with SQL Server 2005, so around 20 years ago, Microsoft provided us optimistic concurrency. And the idea of optimistic concurrency in SQL Server is just the fact that the reader, a select statement, doesn't acquire a shared lock anymore. So every time when you change a record in SQL Server with optimistic concurrency enabled, the old version of that record is written into the version store, which is stored in DempDB. Means when you read a record, the select statement just transparently reads the correct version of that record from the version store in DempDB without acquiring a shared lock. Means with optimistic concurrency, a reader doesn't block a writer doesn't block a reader, and a writer still blocks a writer, and a reader can't block a reader. And Postgres is more or less just doing the same approach, but with a different implementation. We will talk about that later. So Postgres is just using multi-version concurrency control. Means with Postgres, you have no pessimistic concurrency. It's just not implemented. So this is very, very important. You can't have pessimistic concurrency with Postgres because it's just not implemented in the relational database engine. We also have a write ahead logging, means when your Postgres instance just crashes, it doesn't really matter because based on the write ahead log, so the transaction log in SQL Server as we know it, we can recover that database, and the same thing applies to Postgres. You can perform backups, so you can perform backups of your databases, backups of your write ahead log, works more or less from the conceptual perspective as in SQL Server. You have built-in fault tolerance, means you can scale out Postgres, and you also have a so-called asynchronous replication. In asynchronous replication, you have two different kinds of replication. You have a physical replication. You can compare physical replication to always on availability groups. And you have also a so-called logical replication where you can replicate dedicated tables. So logical replication is more or less the replication stuff that we know from SQL Server. So let's switch now over. I already wanted to say let's switch over to SQL Server, but no, today we are switching over to Postgres, and let's do the first few steps with Postgres. I'm running here Azure Data Studio. And the cool thing about Azure Data Studio is just the fact that you can also connect to Postgres instances. So with Azure Data Studio, you are not limited to SQL Server instances. No, you can also connect directly to Postgres instances. On my machine here today, I have deployed Postgres in a Docker container. So when you want to work with Postgres in a Docker container, it's quite simple. You do a docker bool Postgres command, means you're booling the official Postgres command. Takes a few minutes based on your internet bandwidth, and then you just do a docker run command and you instantiate that Docker image. So in my case, I have already done that. I have given my Docker container a name, Postgres. You set your password with an environment variable. So more or less, you're just doing the same thing as when you're deploying SQL Server in a Docker container. We do a port mapping. Postgres is listening on the port 5432, 5432. As we know, SQL Server is listening on the port 1433, so this is already a differentiation to SQL Server, and I'm just running that Docker container in the detached status, and I'm using here the Postgres image that I have downloaded. So when we go to the command line, when I'm doing a docker bs-a command, you can see that Postgres container is already up 3 hours. And I have already connected here to that Docker container. The first thing that you see, we have in Postgres a database called Postgres. This is, from the conceptual perspective, our master database. So this is already very, very important. When you create a connection to your Postgres instance, you always have to specify a database. And therefore, we have here the Postgres database, and we have also a few system databases, template 0, template 1. Those are more or less the model database of SQL Server, means when you create a new database, Postgres just makes a copy of one of those template databases. As you can see, you have here no database like MSDB, and there's also no TempDB database. This is also very, very important. We will see later how Postgres stores your data in the storage subsystem. So let's create a new database. The first very, very important part is that each SQL statement must be terminated by a semicolon. This is already very, very important. You can do the same thing in SQL Server, but in some specific cases, you don't need an ending semicolon in SQL Server. In Postgres, you always need a semicolon. So this is also very, very important. And Postgres doesn't support the Go command. The Go command in SQL Server is not really part of SQL Server. More or less, the Go command is part of SQL Server Management Studio, and this is the so-called batch separator, which you can also change in SQL Server Management Studio. But a Go batch separator is not supported in any way in PostgreSQL. So this is already very, very important. So let's create a new database. When we do a refresh, you can see we have here now our test database. I'm currently connected to the Postgres database, as you can see here. And let's try now to go into that database that I have created here. In SQL Server, we know we have the use statement so that we can change the database context. In Postgres, the use is not implemented, not supported. As you can see, when we try to change the database context, this doesn't work. Means a connection is always bound to a specific database, and when you have connected to a specific database, you can't change that database context anymore. Means we have to change it here. So we are now in test database 1, and now let's create a simple table, nothing special here. The same thing would work in SQL Server, just a table with 4 columns. Let's insert a record into that table. Also, same thing as in SQL Server, and of course the select statement also works the same as in SQL Server. The only differentiation is, as I have already said, you need a terminating semicolon. So this is very, very important. We can also retrieve more information about objects that we have created in our database. As we know from SQL Server, we have all those sys dot views, sys dot tables, sys dot databases, sys dot indexes, and so on. They are specific to SQL Server. They are not part of the SQL specification, means Postgres has no idea about all those sys.views. In Postgres, you have all those things in tables which are starting with BG underline, Postgres underline something. We have, for example, the table BG underline class. And as you can see, I'm passing in here the name of my table in the column relation name. A relation in Postgres is nothing more like a table. And with that, we can retrieve more information about that table that we have created. Each object in Postgres has a so-called OID, object identifier. This is just an ever-increasing integer value, a sequence, an object ID. It's the same as the object ID in SQL Server. As we know, each table, each index in SQL Server has an object ID. The same thing is here in Postgres, but here it's an OID, and it's just an increasing integer value. We have a relation name, as I've already said. A relation is a table, and then we have just more information. As you can see, we have the relation size, so the size of our table. As you can see, the size is currently 8 kilobytes. So Postgres also stores all the data on pages. By default, a page in Postgres is 8 kilobytes large. When you compile Postgres from the source code, you could also change that page size if you want. So it's up to you, but more or less, normally you're just using the default page size of 8K. You can also see how many tuples we have. A tuple is just a record and the different versions of that record. We will talk about that later, but that's a tuple. So every time when we talk about tuples, we are talking about records and the versions of that record. And we also have pages and of course a lot of other columns. So as you can see, that table is very, very wide. So more or less, as you can see here from that very, very simple demonstration, Postgres is just a relational database engine, and more or less you're just working in the default way that you know from SQL Server with that relational database. Of course, under the covers, almost everything is done differently as in SQL Server. Okay, let's go back to PowerPoint. And let's talk now a little bit more about the architecture of Postgres. The architecture of Postgres is completely different from SQL Server. As we know in SQL Server, every time when we create a connection to SQL Server, that connection gets a worker thread. So SQL Server employs internally a so-called thread pool. You are getting a number of fixed worker threads based on how many CPU cores you have assigned to SQL Server. So a thread is just a lightweight process in an operating system like Windows or like Linux. Postgres has no idea about threads. Means every time when you establish a connection, a session against your Postgres database, that session gets a completely fresh process. In Postgres, we have the so-called postmaster process. This is the first process which is started when we are spinning up Postgres. And this postmaster process is forked every time when we establish a new connection against our Postgres instance. So this is also very, very important. Each user session gets a dedicated background process. So this is a huge difference to SQL Server. SQL Server uses threads for user connections. Postgres is just using whole processes. A second key difference of Postgres is just the fact that Postgres only stores our data in heap tables. Just think about it. In SQL Server, we always say heap tables are bad because in heap tables you have no sorting order. Heap tables are very, very slow for reading because you have no sorting order. In heap tables you have bookmark lookup operations and everything. When you access non-clustered indexes, in SQL Server performs lookup operations. So heap tables are very, very bad in SQL Server. But in Postgres, we only have heap tables. There are no clustered indexes. Postgres has no idea about clustered indexes. Postgres has no idea about clustered tables. So all the data that you are storing in Postgres is unsorted. So this is a huge difference to SQL Server. And as I've already said, Postgres has no idea about shared logs for reading. Postgres has no implementation of a pessimistic concurrency model. There is no implementation, means in Postgres you can't have dirty reads. Just think about it. In SQL Server, we all know that query hint with no log means when we read a record in read committed, we just don't acquire a shared log for reading, means we can read uncommitted data. In Postgres, it's not possible. It's not implemented because Postgres is just using by default optimistic concurrency. So more or less the same thing that was introduced back with SQL Server 2005, multi-version concurrency control. So every time when you change a record, Postgres just creates a new copy of that record, a new row version. So an existing row version in Postgres is never ever changed. Every time when you do a change, an update statement, a new row version is generated. This sounds great. Yes, it is great. It has a lot of advantages, but as we will see later, there are also some disadvantages that you have to know when you are working with that multi-version concurrency control system. And as I've already said in the beginning, we also have a transaction log in Postgres. It's called the val log, write ahead logging. So more or less, Postgres is doing the same thing as SQL Server. When you commit a transaction, Postgres has to write all the corresponding transaction log records from the val buffer in main memory to the transaction log. And after that log flush, Postgres can commit that transaction. Means when afterwards Postgres crashes, it doesn't really matter because we have our transaction log records in the val log physically in our storage subsystem. As we know from SQL Server, in SQL Server, we have database files, our MDF file and secondary data files, and we have a transaction log. Postgres is completely different here. In Postgres, there is only one val log across your whole Postgres instance. Means you have one transaction log across all your databases. So this is also a huge difference in SQL Server. You can't crash recover just one specific database. No, you can only crash recover your whole PostgreSQL instance. The name instance is here also wrong. The instance is the so-called Postgres cluster. So every time when I'm talking now about Postgres cluster, it's just the same as a SQL Server instance. A Postgres cluster can host multiple databases and they all share one transaction log, the so-called val log, which is also stored physically somewhere in the file system. We will see that later. So as you can see from that architecture slide, we have our client applications, like in our case, Azure Data Studio. And every time when we create a connection against Postgres, we are starting up a new background process. We have that postmaster process, which is spinned up as soon as we are starting up Postgres. And every time when a new connection is established, that postmaster process is forked, means we create a copy, and that copy, that forked process is used to serve the queries for that specific client application. We have different memory regions in Postgres, more or less the same thing as with SQL Server. Shared buffer is the buffer pool where we cache pages in main memory that we have read from our storage subsystem. But Postgres is here working differently as SQL Server because SQL Server just bypasses the file system caching of the underlying operating system, so Windows or Linux, but Postgres relies on the file system caching. Therefore, the shared buffer is normally configured with much lower values as when we configure the maximum server memory setting in SQL Server. We have also the so-called val buffer. This is just the transaction log buffer in main memory where Postgres writes transaction log records, and as soon when a transaction gets committed, that val buffer must be flushed to the file system, and afterwards the transaction can be committed. We have also a memory region called work memory. Those are just the memory grants that we know from SQL Server. So when you have execution plans with sort, hash operations, SQL Server needs memory grants. The same thing applies to Postgres, and that memory is taken from that work memory region. And of course, in Postgres, you also have maintenance activities which are running in the background. They also need memory, and that memory is taken from the maintenance work memory region. And as you can also see, we have here a lot of different background processes. I have just illustrated here the most important ones. There are much more background processes involved in the overall architecture of Postgres. On the right-hand side, on the top, we have the checkpoint process. Checkpoint process runs in regular intervals and just writes all dirty pages from the shared buffer back to our storage subsystem. You also have the background writer, which is doing more or less the same thing. It just helps the checkpointer. You have the val writer, which is used for flushing transaction log records. And you also have the so-called archiver, which is used when you perform, let's call it, transaction log backups. When you are backing up your val files, your transaction log files, then you are using the archiver. The archiver is disabled by default, means by default your val files, so your transaction log files are not backed up. So this is also very important here. So let's have a look on all those things in a little bit more detail. Let's switch over to Azure Data Studio. And let's have a look now on the architecture of Postgres. As we know from SQL Server, when we are installing SQL Server, we can define in which folders we are putting our database files, our transaction log files. Each database consists of the primary data file in SQL Server, the MDF file. You can have multiple secondary data files with the extension NDF, and we have the transaction log file with the extension LDF. Postgres is completely different. Postgres stores all your individual database objects, so tables, indexes, and so on, in different files. Let's have a look on that one. I'm using here the docker execute command to connect to my Docker container in which Postgres is running. Means, as you can see, my command prompt has changed. I'm now in the context of my Docker container. And a very important folder in Postgres is the folder bg data. In that folder, Postgres is storing all the data of your Postgres cluster. As I've said, the Postgres cluster can store multiple databases. And as you can see in my Docker container, that bg data environment variable points to the folder farlib PostgreSQL data. So let's go into that folder. Let's do an ls command, and as you can see, within the bg data folder, you have a huge amount of subfolders and also a huge amount of different files. Let's have a look on a few things. Very important file is the file bg version. Let's have a look into that file. It just shows which version of Postgres you are running. I'm running Postgres 17. Easy to retrieve. Just look into that file bg version. As I've said previously, when you're spinning up Postgres, the first thing that happens is that Postgres is starting up that postmaster process from which other background processes for user connections are forked. You have here also a file called postmaster pit, and that file just contains a few things about the postmaster process. For example, the process ID, the bit. So in my case, we have here the bit of that postmaster process, bit 1. So this is the process ID. You can see the BG data folder. You have the board on which Postgres is listening and a few other things. So also very, very important. A very important file is the file PostgreSQL conf. This is a text-based configuration file of your whole Postgres cluster. So in Postgres, there's nothing like a SQL Server configuration manager. You don't have server settings that you can change directly through a UI. So all the configuration changes are done in that file, PostgreSQL conf. Let's have a look into that file. I have opened that in a text editor, Nano in my case. And as you can see, that file is huge and that file contains a lot of different information. As you can see, connections and authentication. You can see on which IP addresses your Postgres cluster is listening on, how many connections you can establish. As you can see, by default, you can only have 100 connections with Postgres. So normally when you're working with Postgres in larger environments, you need a connection pooling mechanism. There are tools like BG Bouncer and so on, with which you can reuse connections. So when we go down a little bit more, you can see the shared buffers. By default, we have a buffer pool, a shared buffer of 128 megabytes. Just think about it. This is very, very low in comparison to SQL Server. But as I've said previously, this doesn't really matter because Postgres is using the file system cache. SQL Server is always making direct I/O operations, means SQL Server always bypasses the file system cache of the underlying operating system. Postgres isn't doing that, and therefore the shared buffer is much lower as in comparison to SQL Server. Let's go down a little bit, but as you can see, we have here information about the write-ahead locking and so on. So a huge amount of information. You can see maximum file size, 1 gigabyte, and so on. So all the configuration of Postgres is just done through that configuration file. You have here also nice commands, and in the worst case, just look into the source code. You have here more information about query tuning. As we know in SQL Server, we have a huge amount of trace flags. A lot of trace flags are just undocumented. Here with Postgres, those are just flags. So for example, you can enable index scans, nested loop, merge joins, parallel hash joins, and so on. So more or less, Postgres is in some way much more convenient as SQL Server because you can configure much more things in much more detail. We have also in Postgres a so-called query planner. The query planner is nothing more than the query optimizer in SQL Server. So you can even assign here cost factors. How much costs it to access a page with sequential I/O? How much does it cost to access a page by random I/O? So when you are using spinning hard drives, random I/O is much more expensive than sequential I/O. When you're working with superfast SSD drives, random I/O is more or less the same thing as sequential I/O. So you can help here the query optimizer, the query planner, by tweaking those cost factors. Just think about it. This is really, really amazing on one hand, but on the other hand, really, really scary, because when you change here something, you can just screw up the whole query planner. Just think about it. So this file, PostgreSQL conf, a very, very important one. Another one, which is also very important, is BG HBA conf. When you are setting up Postgres, Postgres isn't accessible over the network. It's just locked down by default. It's the same with SQL Server. When you're installing SQL Server, the TCP/IP protocol is disabled by default, means you have to explicitly enable it in SQL Server Configuration Manager. The same thing applies to Postgres. Postgres by default is only accessible through the machine on which Postgres is running on. Therefore, you have to change everything within that file so that Postgres is also accessible through your network. So this is also very, very important. When you're just deploying, like in my case, Postgres in a Docker container, Postgres in the Docker container is only accessible on that machine where Docker is running, but it's not accessible through the network. So this is very, very important here. So those are the most important files. We have here also a lot of different subfolders, as you can see. bgval, no idea how I should pronounce it. bgval, this is the subfolder in which the write ahead logging occurs. So in this subfolder, Postgres is just storing all the incoming transaction log records from your transactions, from your insert, update, delete statements. Just think about it. Whoops. Let's go into that folder, bgval. As you can see, we have here a huge amount of WAL files. Each WAL file has a size of 16 megabytes. Afterwards, when the 16 megabytes are written, Postgres just creates another file with 16 megabytes. So this is your whole transaction log across all your databases. As I've said previously, in Postgres, you don't have a transaction log on the database level. We only have a transaction log on the cluster level. So this is very, very important here. And another very important folder is the base folder. In the base folder, Postgres stores all your databases with all the database objects, tables, indexes. Let's have a look into that folder. As you can see, we have here a few subfolders. We have here a subfolder with a name 1, with a name 4, with a name 5, and with a name 16445. Those are the OIDs, object IDs, of the corresponding databases. So each database that you create on your Postgres cluster gets in that base folder a subfolder. Let's have a look on our databases. I'm using here the table BG database. And as you can see, our test database 1 that we have created previously has an OID of 16445. That one here. Let's go into that subfolder 16445. Let's do again a list command. And as you can see, we have here now a huge amount of files. So in each file, Postgres stores some database object. System tables like BG database that we have seen, BG class. Postgres stores the tables that we have created and all the indexes that we have created. Each file name is again the OID of that database object, like 1247. You have here also other files. We have a so-called free space map. The free space map is the same thing as the page free space of a heap table in SQL Server, the PFS page, where SQL Server just stores how much free space we have on the different pages on a heap table. So Postgres is doing here the same thing with the so-called free space map. We have also a file underlined VM, that's the so-called visibility map. The visibility map is used for multi-version concurrency control and just define which double versions are visible to other transactions. Let's create a larger table. So I'm creating here a new table. As you can see, you can use your primary keys. ID generated means we'll just create an auto increment column int identity in SQL Server. And I'm inserting here 30 millions of rows. This takes now around 60 seconds. So if there are some questions, just go ahead. Otherwise, I'm just talking, but if you have no questions, just go ahead. So when Postgres is storing data in the file system, a file can't exceed a file size of 1 gigabyte. So as soon as we have written 1 gigabyte of data into such a file, Postgres just creates an additional file for that database object. So in our case, when we are inserting here 30 millions of rows, the table has a size of around 1040 megabytes. In the meantime, we can also go to htop, and as you can see, we have here now background processes. As you can see, we have here background processes, and one of that background processes was the session with which we have inserted those 30 millions of rows. So this is now finished. So when we check now the size of that table, I'm using here again bg underline class, you can see now we have around 1040 megabytes, and we have an OID of 16450 for that table. So let's do again an ls command, and let's search for 16450 star. And as you can see now, we are getting back 3 files. We have two, let's call them data files. The first data file, we have written 1 gigabyte. And we have a second data file with the extension .1. Means the first gigabyte was written to the first file, and the second gigabyte is now written to the file with the extension .1. When we have written 2 gigabytes of data, we create an additional file .2, afterwards .3, and so on. So each file just has a maximum size of 1 gigabyte. So this is also a complete differentiation to SQL Server. In SQL Server, we have one huge data file, or maybe you use multiple data files, and SQL Server is spreading the data in a round-robin fashion across all those files in a file group. But here in Postgres, each database object is stored in a separate file, and each file can only have a maximum size of 1 gigabyte, and afterwards we are getting an additional file. So SQL Server more or less implements its own file system inside the MDF file, and Postgres just relies on the underlying file system of the operating system. And in addition, we have here the free space map, which just defines how much free space we have in that heap table. As I've mentioned previously, we have only heap tables. There are no clustered indexes, clustered tables available. Cool. Let's go back to PowerPoint. So let's talk now a little bit more about querying data. When you know me, you know I have done in the past a lot about performance tuning, performance troubleshooting in SQL Server, and one of my main topics was always, or is always, indexing. And the first time when I have looked into Postgres, I have thought, oh my God, this will get really, really complicated because Postgres is so different from SQL Server, from the architecture and everything. But trust me, Postgres, it's just a relational database. When you know how indexing works in SQL Server, you doesn't need that much time to migrate your knowledge over to Postgres. Postgres more or less is just doing the same thing from an indexing perspective as SQL Server. I'm always telling my wife, yeah, I'm working with a new database, but it doesn't really matter because it's just a relational database. It's the same thing when you're buying a new car. You don't need to renew your driving license because you know how you drive a car. And it's the same when you're working with a relational database. You are not starting with zero knowledge. You already know how a relational database works, and therefore it's quite easy to work with a relational database. So let's have a look in the first step how our data is stored. As I've already said, forget about clustered indexes. Forget about clustered tables. Postgres is always storing our data in heap tables. So this is very, very important. There is no support for clustered indexes. We are just storing data unsorted in heap tables. In Postgres, you have a command called cluster with which you can sort the data. But the sort order afterwards is not maintained. Means when you run the cluster command, the data in your table is sorted based on the columns that you have provided to the cluster command. But afterwards, when you perform insert, update, delete statements, the sort order is not maintained anymore. So more or less, you just work without a sorting order in Postgres. And we have different kinds of indexes available. The cool thing about Postgres is, as I've already said, it's open source. If you have a cool idea about the new index that you want to implement, just go ahead, you can do that. In Postgres, we have so-called access methods, and they are extensible, means you can provide your own indexes, and the query planner, the query optimizer, will be afterwards able to use those indexes that you have implemented for Postgres. So Postgres is very, very extensible. In Postgres, you are working very, very often with so-called extensions, means you can extend the code base of Postgres. And this is very, very powerful. In SQL Server, we can also extend the code base by working with user-defined functions. You can work with SQL CLR, but in Postgres, it's much more powerful, and in no way you can compare that extensibility options with SQL Server. So we have different kinds of indexes. And those indexes are just able to retrieve the data from heap tables in a more efficient way. In the worst case, you're just sequentially scanning the heap table. That's a so-called sequential scan in Postgres. The sequential scan is the same thing as a table scan in SQL Server. If you want to speed up a table scan, a sequential scan, you can create a B-tree index. The B-tree index is more or less the same thing as a non-clustered index in SQL Server. You can also define hash indexes. SQL Server also supports hash indexes, but only in combination with memory optimized tables. In Postgres, you can define hash indexes just on each table. Postgres has no idea about memory optimized tables and disk-based tables. We have just heap tables, and on those heap tables, you can also define hash indexes. And there are also more other indexes. I haven't yet looked into the details of those indexes. GIST, SB GIST, GIN, WAM looks cool or sounds cool. But those indexes are mostly used when you're working with geometric data types within Postgres, or when you're working with full text search. But more or less, when we just concentrate on OLTP workloads, you're mostly working with D3 and hash indexes. Let's have a look now on query plans. As we know from SQL Server, SQL, the programming language, is just a declarative programming language, means we are describing the database, the data that we want to retrieve, and the query optimizer compiles a physical execution plan, and the physical execution plan, the query plan, is just a computer program that the relational database runs when we afterwards finally retrieve that data. As I've already said, the query optimizer in Postgres is called the query planner, and the query planner compiles you also for your declarative SQL query a physical query plan. So the query plan is the execution plan. In SQL Server, we say execution plan. In Postgres, we say query plan. Just a different wording, but it's just the same concepts. Of course, we also have statistics in Postgres, means statistics are describing the data distribution of columns to the query planner, to the query optimizer, and based on the data distribution, the query planner is able to compile a good query plan for you. We have also two kinds of plans in Postgres. We have the estimated query plan, means that's the query plan which is generated by the query planner without executing the query. The estimated query plan can be retrieved by the explain command. And we have also an actual query plan. This is our actual execution plan. And that query plan also contains runtime information about your query, because when you use the explain analyze command, the query is also running, and afterwards, in our case, Azure Data Studio returns you the actual query plan. So more or less, query plans are working the same as with SQL Server. We have the estimated and we have the actual query plan. You can also analyze query plans. So when you use the explain command, you can also specify a format. There are different formats. By default, when you just use explain select blah blah blah, the default format is text. This is the text format that you maybe know from SQL Server 2000 and older versions. Even today in SQL Server 2022, I think SQL Server still can return your execution plans in the text format, but it's not really used anymore, because in the SQL Server world, we just work with graphical execution plans. In Postgres, there are no graphical execution plans. Just think about it. More or less, you mostly work with the text format. In the first step, this was really, really painful for me. But afterwards, after a few days and weeks, it is really, really powerful, trust me. And in addition, you have also the possibility to retrieve query plans in different formats, in JSON, YAML, and in the XML format. And the cool thing is, when you retrieve your query plans in JSON, for example, you can use other tools to visualize those query plans. And one tool that I'm mostly using is on the website explain.talibo.com, where you just paste in the JSON of your query plan, and then you get a graphical representation of your execution plan, which is more or less the same thing that you know from SQL Server. But again, it's much more powerful than the graphical execution plans that we know from SQL Server. I have here a picture. I will also show you afterwards an execution plan. But more or less, you see here again, a traditional execution plan. You have multiple operators in that execution plan. Each operator performs a specific task, returns rows to the next operator, and finally, the top operator, the last one on the top, just returns the result back to your client application. The only difference is when you look on that execution plan in SQL Server, we are reading execution plans or SQL Server executes. No, we are reading execution plans from the right to the left. When you look on that picture, you are interpreting that picture from the bottom to the top. Means the bottom operator is the first operator that gets executed, and the top operator is the last operator. So in SQL Server, the last operator is the select operator, and this operator is here on the top of that query plan. So more or less, when you're working with that tool that visualizes execution plans are just rotated by 90 degrees. In SQL Server, we are reading execution plans from right to left, and in Postgres, we are just reading execution plans from the bottom to the top. Doesn't really matter. More or less, it's the same. I have also listed here the data access methods that Postgres can use with B-tree indexes. As I've mentioned previously, the B-tree index is more or less the same as the non-clustered index that you know from SQL Server. When you don't have any B-tree index on a heap table defined, the query planner is using a sequential scan operator. The sequential scan is more or less the table scan operator, means we are reading the whole heap table, and maybe we are evaluating an additional search predicate. As inefficient as possible, means the more records you are getting, the longer the sequential scan takes. So it doesn't really scale with the amount of the data. When you have for your search predicate an index scan, a B-tree index in place, Postgres can use an index scan. The index scan is more or less the same thing as a non-clustered index seek in SQL Server, or non-clustered index scan in SQL Server, means we are reading the whole index, and for each qualifying record that we get in the leaf level of that index, Postgres performs a lookup operation against the heap table. Yes, you heard correct. Postgres performs for each qualifying record a lookup operation against the heap table, because in the B-tree index, you just have a subset of the table data. When you have requested in your select statement more data, and those columns are not part of that B-tree index, you have to go to the heap table. So you perform a lookup operation. But that lookup operation is not part of the execution plan because it is part of the index scan operator. So this is also a huge difference. When you're working with B-tree indexes in Postgres, you're performing lookup operations more or less very, very often. This is just your effect of Postgres. In SQL Server, we say lookup operations are bad. In Postgres, they are just done very, very often. When you have a covering B-tree index, means you have a B-tree index defined, and for a query, each column is part of that index, then Postgres can perform an index-only scan. So an index-only scan means that no lookup operations are necessary because all the data that we have requested in our query is part of that B-tree index that we have defined. So more or less the same thing as a covering non-clustered index in SQL Server. And in addition, and this is a completely different access method that doesn't exist in that way in SQL Server, is the so-called bitmap index scan. A bitmap index scan is used very, very often when you return or when you request a smaller amount of data from your heap table. And the bitmap index scan consists of two phases or two operators. In the first phase, we have the so-called bitmap index scan, and the bitmap index scan just builds a bitmap based on the tuple IDs that matches your search predicate. So for each page that we are requesting, we are getting a bit in that bitmap, and that bit is set to 1, means we request that page. And afterwards, that whole bitmap mask is handed over to a second operator called the bitmap heap scan, and that operator just reads all those pages where the bitmap or where the bit in the bitmap map is set to 1 and reads those pages from the heap table. Means you only need to access each page once. And this is much more powerful as in SQL Server, because in SQL Server it can be the case that you are reading a page over and over and over again when you're accessing different records. And with the bitmap index scan and bitmap heap scan, Postgres avoids that problem. In SQL Server, we also have bitmap scans, but only in combination with parallel execution plans. Here in Postgres, bitmap index scans are also working with serial execution plans. So execution plans which are just running with one process. There are no worker threads. Even Postgres supports parallel execution plans, but parallel execution plans means you are spinning up multiple processes for one execution plan. So let's have a look on that one. I create here a new table, and I'm inserting into that table 100,000 records, and I'm creating on the first column, column 1, which is an integer column, just an index. So you have to create index statement, you give that index a name, so more or less the same thing as in SQL Server. You define the table and the column or the columns. And in addition, I'm just running the analyze command on that table, and this is more an SB update statistics. I'm just making sure that the statistics are just up to date so that the query planner can choose the best possible execution plan for us. When we look into that table, you can see we have here data. And now let's do a count star. As you can see, we have 100,000 records. And with the explain command, we can request now the estimated execution plan or estimated query plan without running the query itself. So this is just the estimated execution plan. And as I've said, by default, you're getting back an execution plan, a query plan, just with text. It's just text. Each operator has that error. So as you can see, we have here in sequential scan. Sequential scan is just a table scan in the SQL Server world, and you have your aggregate. In SQL Server, this would be a stream or hash aggregate, depending if you are working with sorted or unsorted data. So even that textual query plan is read from bottom to the top. So in the first step, in the logical way, we execute the sequential scan, the table scan, and afterwards we aggregate those rows together. You can see each operator has a cost factor. We can see how many rows we are retrieving. You have a row width. So all the information that you already know from the tooltip window in SQL Server. And when you use the explain analyze command, Postgres is running the query and returns you afterwards the actual query plan. The only problem that I'm having here with Azure Data Studio is the fact that you only see the query plan, the actual query plan, but Azure Data Studio doesn't show you nowhere the data itself, but the query was running. So as you can see, we are getting here much more information. You have the planning time. The planning time is the time that the query planner, the query optimizer, has used to generate that query plan for us. So around 124 milliseconds or 0.124 milliseconds. You have the execution time. So the whole query execution took around 7 milliseconds. And you can also see here more information. As you can see, we have here now actual time. So more or less, again, the same thing as in SQL Server. In the estimated execution plan, we have estimations. And in the actual execution plan, we also have actual properties like actual number of rows returned and so on. Let's have a look on the different access methods. I'm returning here just one record. With one record, the query planner has chosen an index scan. Index scan is the same as a non-clustered index scan or non-clustered index seek. Means we are only reading from the non-clustered index, and for each qualifying row, you can see we have here an index condition check, and for each qualifying row, Postgres performs internally a lookup operation. This is the row identifier lookup operation in SQL Server. But you can't see those lookup operations here. So this is also very, very important. You perform internally lookup operations. I have here second query. I'm returning here 199 rows, means we're already getting more rows. We're getting more and more rows. With 199 rows, you can see now that the query plan has changed. We have now that combination of a bitmap index scan on that index in combination with a bitmap heap scan. So the bitmap index scan just calculates which pages we need to access. It generates a bitmap in memory. For each requested page, the bit in that bitmap is set to 1, and afterwards the bitmap heap scan reads those pages where the bit in the bitmap mask is set to 1, and then just rechecks the condition. And with that approach, you are able to read each page just once, even when you request multiple rows from the same page. So this is one data access method that isn't implemented in any way in SQL Server. So this is really, really powerful here. Let's create an additional index on the second column. Means we have now two indexes. One index on column 1 and the second index on column 2. As we know from SQL Server performs an index intersection in this case very, very often. The index intersection in SQL Server is done with a physical join operator, nested loop, merge join, or hash join. In Postgres, the index intersection is done in a completely different way. As you can see, we have a bitmap index scan on the first column. We have a bitmap index scan on the second column. Means each bitmap index scan generates a bitmap mask, and then we are just ending those bitmaps together. So we have a final bitmap mask, and that final bitmap mask is handed over to the bitmap heap scan. And again, the bitmap heap scan just reads those pages that we have requested once. So this is also really, really powerful. So this is more or less an index intersection just done in a different way as in SQL Server. You can also specify the format. So for example, when we run that, we are getting back our execution plan in JSON. Let's copy that to JSON. And I'm going now over to explain Talibo.com, and you can paste in your query plan data. You submit that. You get a warning. The plan will be sent to the server and stored in our database. So when you have sensitive data in your query plan, be aware of that. You can also install that tool Talibo locally. Means when you have sensitive data, just run it locally. Very, very powerful, just works out of the box. So let's confirm that. And as you can see, now we have a graphical execution plan. This is more or less the same thing as in SQL Server, but we have just rotated the execution plan by 90 degrees. So we have the two bitmap index scans on the bottom. As you can see, you have here a cool description, which you also don't have very often in SQL Server. Afterwards, the input of those bitmap index scans are fed into the bitmap AND operator, and finally, the bitmap heap scan returns the final result. So this is just a graphical way to show the execution plan. So normally in my case, I'm mostly working with textual execution plans to get in the first step a better understanding, and for more large or complicated execution plans, I'm finally handing over the JSON data to that tool to get a better representation. Let's run that query again. We are returning now almost 60,000 records. And with 60,000 records, the query planner changes the execution plan. We have now the sequential scan with a filter condition. So we perform now the table scan because the bitmap heap scan isn't efficient anymore. It's the same as the tipping point in SQL Server. The more and more rows you are returning from a table at some point in time, the query tips over, and instead of accessing a non-clustered index and performing expansive lookup operations, the query optimizer decides to use a clustered index scan or a table scan operator. And the same thing applies here in Postgres. And we also have the so-called index-only scan. In that query here, I have used the select star command. We have a few columns in that table. Therefore, when you access or when you have only indexed one column, you need the lookup operations in the background. In that case here, I'm only selecting column 1, and column 1 is part of the index that we have created earlier. So more or less the index that we have created on column 1 is for this query a covering index. And in that case, when Postgres has a covering index, then we perform an index-only scan. And the index-only scan means we only access the B3 index without reading data through lookup operations from the heap table. So this is your index-seek non-clustered or index-scan non-clustered operation without any lookup operation. So more or less, the query planner in Postgres is doing the same thing as the query optimizer in SQL Server, but it is a little bit more powerful because you also have the possibility of those bitmap operations that we don't have in SQL Server. SQL Server only employs those techniques in parallel execution plans. Cool. Let's talk now for the last few minutes. I know that I'm already a little bit late, but I really love to talk today. Let's talk now for the last final minutes about the multi-version concurrency control system in Postgres. As I've already said in the beginning, Postgres has no idea about pessimistic concurrency. Means in Postgres, there's no implementation of acquiring shared logs for select statements. There is no code path available which acquires shared logs when you run select statements. Means dirty reads are not even possible by design. Just think about it. A query hint with no log, it's not there in Postgres because it's not needed. And there's also no isolation level read uncommitted. Of course, the isolation level read uncommitted is part of the ANSI SQL specification. So you can still set your isolation level to read uncommitted, but Postgres is just behaving as in the isolation level read committed. So in Postgres, you have 3 different supported isolation levels: read committed, repeatable read, and serializable. But every time with optimistic concurrency. So this is very, very important here. How does multi-version concurrency control work? As I've already said previously, when you have inserted a row into a heap table, that row gets never changed anymore. So when you perform an update statement, Postgres just generates you a new version of that row. So Postgres is doing more or less the same thing as SQL Server with optimistic concurrency, which was introduced back with SQL Server 2005. So each row in Postgres has 2 internal columns called xmin and xmax. Xmin is the transaction insert ID, so more or less the timestamp when that row was inserted into that table. And the xmax column is the transaction delete ID, so more or less the timestamp when that row was deleted. So when you perform an insert statement, Postgres populates the xmin column with your current transaction ID, which is just an ever-increasing integer value, and the xmax column is set to null or 0. This is an insert. When the xmax column is null, it means this is the current version. When you delete a record, it's quite simple. You update the xmax column to your current transaction ID. So more or less, you're just terminating that row version. That row was valid from xmin to xmax. And when you update a row, it's quite simple. The first step, you delete the row, and afterwards you insert a new version. That's it. But in Postgres, we don't have a DB. In Postgres, we don't have a version store. All those new row versions are stored directly on your heap table, on your pages of 8 kilobytes. So when you perform a lot of update operations, you're generating new row versions, and those row versions are stored directly in your heap tables. So your tables are getting bloated over the time. They are getting larger and larger and larger. I will tell you later how you can fix that problem. This is called table bloat. So every time when you perform update operations, you're generating just additional row versions. Some of those row versions are still needed because you have some concurrent transactions which are referencing those row versions, but some row versions which are in the past, they are not needed anymore. In SQL Server, we have the same problem with the version store. In SQL Server, we have a cleanup process which runs periodically. That cleanup process goes over the version store and just discards row versions that we don't need anymore. In Postgres, we also have such a cleanup process. It's called auto vacuum. It's a background process which also runs regularly, and that background process just removes unnecessary row versions, so row versions which are not referenced by any transactions anymore. And with that, you can make your tables smaller again. And we also have a manual vacuum command, which you can run interactively just to get rid of older row versions manually when you don't need them anymore. So let's have a look on that one. Let's create a new table. And what I'm doing here is now the following. I'm beginning a new transaction and I'm inserting into that table a new record. And then we return with the function bg current transaction ID, the current transaction ID. And as you can see, I'm also showing you from that table the xmin and xmax columns. Those are just internal hidden columns. As you can see, we have a current transaction ID of 813. It's just an ever increasing integer value. And this is our current row version. So as you can see, our xmin is 813, the time when we have inserted that record, and xmax is 0. Means this is our current row version. And we have begun a new transaction, and this transaction is not yet committed. Let's open a new query window and let's try to read from that table. This statement doesn't block. So as you can see, we can run without blocking, but we just doesn't get back any result. Makes sense because we haven't yet committed that transaction. When we now commit that transaction and we run our select statement again, you can see now we can see that row version because now it is a committed row version. Previously, when we would have seen that row version, that would be a dirty read, but dirty reads are technically not possible in Postgres. Let's work with update statements. Same thing. I'm beginning a new transaction. I'm changing the second column of that record. We look on our current transaction ID and we check the xmin and xmax columns. So as you can see, our current transaction ID is now 814. It's just an ever increasing integer value, nothing more. And our xmin is 814, xmax is 0. When we run now our select statement in SQL Server with a parallel write activity, that statement would block with pessimistic concurrency. Here with multi-version concurrency control, it doesn't block. We're just returning the old committed version, which is stored directly on our heap table. There's no version store involved. So the page of 8 kilobytes has now two row versions. The first one that we see here in the second transaction and the second row version that we see here. We have just two row versions. And based on the current transaction ID, Postgres returns you here the older committed version. When we now commit our update statement, our current row version is Klaus Aschenbrenner. So when we run that statement again, you can see we see now the newer version. But the older version from 813 to 814, where call 2 is Klaus, is still on that page. Means on larger tables, when you're performing a lot of update statements, your tables are getting larger and larger and larger over time. So we have committed that transaction. Let's talk about deletes. I'm beginning again a new transaction. We delete all the records from that table with a transaction ID of 815. Our table is empty, but the second transaction doesn't see that empty table because the transaction isn't yet committed. Means when we finally commit it, we see the empty table. So this is the default behavior of the isolation level read committed with optimistic concurrency or multi-version concurrency control, how it is called in Postgres. So this is really, really powerful because you're not dealing with dirty reads anymore. There is no query hint with no log. And as I've said, you can set your isolation level to read uncommitted because it is a supported isolation level in the ANSI SQL specification. But internally, read uncommitted is just doing the same thing as the isolation level read committed. So this is really, really powerful in Postgres because readers are not blocking writers and writers are not blocking readers. And this concept, it's already there since ages. As I've said in the beginning of that presentation, Postgres, it was released in 1989. This is many years ago. In that year, I was 9 years old. This year, I'm getting 45. 45, yeah, not 54. 45. Just think about it. This is more than 30 years ago. And with SQL Server 2005, 20 years ago, we got optimistic concurrency. But these days, when I'm working with customers, mostly all those people are still using pessimistic concurrency, which is crazy because it leads to so many blocking situations, so many deadlocking situations. And Postgres, since its inception, just uses multi-version concurrency control and therefore avoids a huge amount of different problems regarding concurrency and blocking and deadlocking situations. So more or less, I'm a really big fan of Postgres because it's really, really powerful. As you have seen, there are huge differences in comparison to SQL Server. Some differences are good, some differences, of course, are bad. Especially when you're dealing with high availability, SQL Server is much easier to configure. Postgres is more complicated to configure when you're working with physical replication and everything, but it's more powerful because you can configure it more fine granularly. And for me, the cool thing is Postgres is open source. Means I can look into the source code to get a better understanding how the relational database engine works. And I haven't yet said that today, but this is also very important. Postgres is free. You don't have to pay any cent for Postgres. This is very, very important. You can just use it just for free. When we are talking about SQL Server, especially about the Enterprise, the expensive edition, you are paying a huge amount of money to use those features. Postgres, it's just free, it's just open source. You can do with that source code whatever you want. So I hope that you have enjoyed that session today about Postgres. It was just a quick overview, just about the key differences about Postgres. I haven't yet talked about very details and everything. If you are interested more about Postgres itself, I'm running in April a 2-day long online training with the title PostgreSQL for the SQL Server Professional, where I'm just showing you in 2 days how you can migrate, how you can transfer your existing SQL Server knowledge to Postgres. Means we are talking here in more detail about the key differences between Postgres and SQL Server, query tuning in much more detail, the multi-version concurrency control system. I am also talking about high availability, disaster recovery, replication, backup strategies, just everything to get you up to date with Postgres. You can find more information in that link. Yeah, I hope that you have enjoyed that session today. It was a lot of fun for me to speak the first time in my life about Postgres. So if there are questions, just go ahead and ask. Thank you.
Thank you so much, Klaus. This is great session, especially the to differentiate between SQL Server versus PostgreSQL, and this is a great overview with a lot of demos as well. This is
Thank you.
really great. I learned a lot,
Thank you.
and we are so honored to 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 learn that this is your first Postgres session, and we are honored that you have spoken to our user group here. So I know we are running out of time, but we have a couple of questions here. If you can please quickly go through them, I think that would be awesome. So the first question is from John Deardroff. He asked, like, does the master DB need to be called Postgres, or can it be something else?
No, it's the postmaster process. You can't change that. Maybe in the code base.
Awesome. So the other
So more
question,
or less, you can
yeah,
change everything that you want. You have access to the source code.
yeah, yes, yes, it's free basically. So open source. So the other question is from Manish. He asks, why rel tuples is -1 when we inserted one row in test table one table.
Maybe some internal information wasn't yet updated by Postgres internally. No idea on that one. I have to
Okay.
look into the source code.
Yeah. So the other question is from Alvaro Costa. I know Kendra answered this question, but we want to know your take on this as well.
Mhm.
So why does PG implements read committed as default isolation level?
Read committed is just the default isolation level. Even in SQL Server, when you don't specify an isolation level, the default one is read committed, which prevents dirty reads by default in SQL Server.
Awesome. The other question is from Hugo Alhandra. How do you decide how much memory to allocate to the OS file cache versus buffer cache on Postgres?
This mostly depends on your workload, so you can't say that out of the box. As I've said previously in Postgres, you configure the shared buffer, so the buffer pool in SQL Server with much lower values because Postgres relies on the file system cache. But it depends on your
Awesome.
workload.
Mhm. The last second question was from Tung. Do we have a profiler like Microsoft SQL Server has?
Out of the box, not, but there is a huge ecosystem around Postgres with a huge amount of different extensions, and I think there will be also something like a profiler.
Thank you. The last question from Gregson. Can you query a previous xmin for an updated record?
No, you can't go back in time with Postgres. This is not possible.
Great questions and great answers. Thank you so much, Klaus. And this is a
Thank you.
great session. I definitely have to go back again at least twice. See the see the video twice, not once but twice, to get all the content. But I would like to thank each one of you for staying here to
Hmm.
listen to the entire session. And we are so honored to have you here, Klaus. And thank you so much. And
Thank you.
really looking forward for our next session. Thank you, everyone.
Thank you.
Bye.
Bye.